Hello, everybody. This lecture is the final lecture in the radioactivity series. And so I thought, what better way than to end it with a trip to the sun? We've, of course, visited some other locations that were highly radioactive, but of course, none of them come close to the radioactivity that's occurring here on our sun, the center of our solar system. And while I can't say the same for Chernobyl, there is not a soul around. However, if you think about it, sol is Spanish for sun, and the sun certainly is around. So I guess from that perspective, there is a soul around. Oh. Um, anyway, we've been talking mostly about fission with unstable nuclei breaking down to reach stability. But of course, the sun is a place where nuclear fusion is occurring, right? So we have hydrogen atoms being forged into deuterium, or deuterium being combined with another hydrogen atom for tritium, and then helium-3, and all of these things are coming together from tremendous heat from the sun, right? And this is how all of our naturally occurring elements in the universe were created, in the fiery infernos of the stars, which then eventually burst forth and cast those elements out into the universe. And of course, if I was really this close to the sun, I would instantly vaporize. And if that didn't get me, certainly the radiation would, right? That's coming out of this fusion. We all know that there's visible light radiation, obviously, from the sun. And you're all familiar with ultraviolet radiation from the sun. But there's also things like radio waves and infrared rays, X-rays, gamma rays, all of these things that are also being emitted from the fusion processes that are occurring in this thing. So highly, highly radioactive. And I'm going to actually leave because I'm starting to get a little hot. So let's share the screen and get into the final aspects of radioactivity, and that being kinetics. Okay. And so half-life, you'll remember we were talking about in the context of kinetics, looking at concentrations of reactants and seeing how long it took for that concentration to decrease by half, right? In this case, in the context of radioactivity, we're talking about half-life, meaning the time required for half of the atoms in a given sample to decay. And of course, this is important because we want to know how long some radioactive material is going to last, particularly if it's useful. In the instance of cobalt-60, for example, cobalt-60 is used to treat cancer. And so we want to know how long that radioactive material is going to be effective. Of course, we also want to know how long the bad radioactivity, the bad radioisotopes will stick around as well, right? So half-life is very important for the good and the bad aspects of radioactivity. And, as it turns out, the half-lives of different radioisotopes can vary tremendously, right? For instance, tritium that I just mentioned earlier, H3, has a half-life of about 12.3 years. Other things like P32 or phosphorus 32, which is used to treat leukemia and also used as a a radio label for tissue samples in the lab, it's gone by about 14 and a quarter days. And then, of course, it can go up much higher than that, take much longer for half of a sample to decay. Um, but as you can see here, there's a pretty big difference based on what the radioisotope is that you're looking at or examining. And I'll get into a little bit of why that is the case in just a bit. Here are some half-lives of radioactive isotopes that are used in medicine. So again, the cobalt-60, iodine-131 is also used in to scan thyroids and to look at and to use as a treatment if you have hypothyroid or hyperthyroid or other thyroid issues. And so because it's readily up, I believe it's the thymus that takes up iodine-131 quite readily, at the exclusion of other tissues. So it has a very localized attack. So anyway, look at those at your leisure. You won't be responsible for them on the test. It's just for your own information. Here are just a few examples of just how much radioisotope half-lives can vary. Of course, uranium-238 takes billions of years to decay, whereas carbon-17, which is a very limited and rare radioisotope, breaks down within thousandths of a second. So it can be very, very wide in terms of time. P32 again is about 14 days. So, if we had a 100-gram sample, we could say that 50 grams would be left after 2 weeks, right? That's basically the definition of a half-life. Let's go back to iodine-131 though, right? It has a half-life of about 8 days. So if we were using iodine-131 to treat thyroid problems, we would say that if we used 1 gram of it in 8 days later, so a little bit longer than a week later, there'd be half a gram left, right? And so 1 gram after 8 days goes to 5 grams. And then another 8 days, so a little over 2 weeks, it drops down to 0.25 grams. So each time you're cutting that sample in half from 1 to 0.5 to 0.25, then another 8 days to 0.125, okay? And so we can also think of this in terms of percentage as well, right? It goes from 100% to 50% to 25% to 12.5%, and so on and so forth. And the way we can calculate, for instance, how much of a sample is remaining after a given number of half-lives is to take 0.5 representing, of course, a halving of something. So that's the half-life, taken to the nth power. The nth power, n, just represents the number of half-lives that have occurred in a given period of time, okay? So in this case, if we said that we had 3 half-lives, it would be 0.5 to the 3rd power, which is 0.125, right? And if we started with 1 gram, like we're saying up here, we would say that we would take 1 gram times 0.125, and that would give us, at the end, 0.125 grams, right? Which is what we're basically showing in this diagram above. Okay, and that's how you calculate half-life. Very simple. Let's use it to look at iodine-131 after 20 days. So again, if the half-life is about 8 days, then we say, well, how many half-lives occur in that time that they're giving us? So if they're giving us 20 days, we just simply say 20 days divided by 8. and that gives 2.5. Okay, so that means 2.5 half-lives have occurred in that 20-day duration. And so we simply say that it's going to be 0.5 to the 2.5 power, which is 0.177. Okay, and that's what would be left. Of course, if we started with 1 gram. Let's say we're looking at carbon-14, which I'll talk about later. It's used for radiocarbon dating. And let's say we're looking at a sample that we think is about 17,000 years old. And let's say we know that carbon-14 has a half-life of 5,730 years. We do the same approach where we look at how many times how many half-lives can fit in that duration. So instead of looking at what was it? It was 20 days with iodine-131. We're looking at 17,000 years. And if you divide that by the half-life of 5,730, you get 2.9. Or let's just round it up to 3. So you would say that 0.5 to the n is equal to 0.5 to the 3rd power. And that gives you 0.125. And so you could say that there is 12.5%, because you, of course, to get the percentage, you just multiply by 100. 12.5% of that sample is left. And of course, going back here, 3 half-lives is going to be 12.5%. So it doesn't matter what the actual half-life is or the time that goes by, it's still going to be 12.5% because that's the breakdown from 100% to 50% to 25% to 12.5. Okay. But this is just kind of validating it that actually makes sense and that actually is true and that you can apply that no matter what your radioisotope is or what's going on. That's the question. Or what the half-life is, or how long a period of time that has transpired. Okay, now let's get to business. You guys will remember kinetics based on, what was that? Gosh, a couple weeks ago. And rate laws, integrated rate laws, and how we have these different rate laws for different order reactions, right? So this would be the rate law for a 0 order reaction, a 1st order reaction, and a 2nd order reaction. So integrating that, we get the concentration of A equals a negative KT plus the initial concentration of A. And for a 1st order reaction, we get the natural log of A is equal to a negative KT plus the natural log of the initial concentration. And then for a 2nd order reaction, the integrated law is 1 over the concentration of A equals a negative KT plus 1 over the initial concentration. Okay, so turns out that nuclear decay follows a 1st order kinetics reaction. Okay, and that the intensity of the radiation of a particular radioisotope happens to be proportional to the rate of decay. So the more intensely something radiates, the quicker it'll break down. Okay, and also the more of that sample that's broken down, or how do I say, as more of the sample breaks down, the intensity is going to dampen over time, right? Because they're proportional directly to each other. So both the amount of material and the intensity of radiation decreases by 0.5 in the case of cobalt-60 every 5.27 years, or its half-life, right? So for every half-life of a radioisotope that occurs, you're cutting in half the amount, not just the amount of material, but the intensity of the radiation. Okay. And so when we plot this out, if we're plotting the percentage of cobalt-60, for example, that remains starting at 100%, and we plot it over the number of half-lives, you see that you get this trend here. And this should look a lot like a first order reaction, right? The way it goes down like this, not when we do the integrated rate law and it's a straight line, right? Before it's integrated, it looks like this. It goes down, okay? And that's how we can kind of apply, in a basic way, first order kinetics to nuclear decay. Now, in order to do that, we have to tweak it a little bit. So instead of saying that rate is equal to the rate constant times the concentration, which is the A, right? We replace the A, or the concentration, with N representing the number of nuclei in our sample. We also have to consider what we call the decay rate. Okay, the decay rate is equal to lambda, or sometimes they just, sometimes they just denote it as K. So you'll see you'll see it written as lambda or K interchangeably when looking at nuclear decay. What is lambda? Lambda is the decay constant. So, so we're just taking that rate constant, designating it as a decay constant for a particular isotope. And so that decay constant is going to change based on whatever radioisotope you are examining. All right. Now, if we want to express the decay constant, that lambda, in terms of the half-life, we can say that the lambda is equal, or the decay constant is equal to the natural log of 2 over the half-life, or is equal to 0.693 over the half-life. And hopefully that number looks familiar, because that 0.693 is also the same as the number that we use in first order kinetics for concentrations as well. So bam, something's consistent, which is great. Don't have to memorize a new number for this, right? Now we could also rearrange this to get the half-life by itself, saying that the half-life is equal to 0.693 over lambda. Now, if we wanted to look at the amount, or N, right, the number of nuclei and time, and relate those two, then we have a slightly different equation, right? And ultimately what we'll end up doing is using these two equations together to get the answers, right? So we use this first equation to get the decay constant. And then once we have that decay constant, we can plug it in here, right here, representing K instead of lambda. Because like I said, they're written interchangeably depending on the textbook, but we would have NT equals NO times e to the negative KT, or e to the negative lambda T, if we were solving for NT. Now what's NT? NT is the number of nuclei, or the moles of radioisotope remaining at a given time. Whereas NO is going to be just like AO was the initial concentration, NO is the initial number of nuclei or moles of the isotope before it starts decaying, or before we start measuring the decay. All right. And of course, you can rearrange this equation on the left to solve for T by flipping things around a little bit, okay? And you get T equals negative 1 over lambda times the natural log of the NT over NO. Or really compress this, you could say negative NT over NO over lambda. if that makes sense. It will, because we're going to use these and do some problem solving with them in just a little bit. How about now, actually? So here's a problem from the book, the OpenStax textbook. It's saying that cobalt-60 with 27 protons decays with a half-life of, as we've said, 5.27 years to produce nickel-60 with 28 protons, right? They want us to figure out what is the decay constant, what is the fraction of a sample of cobalt-60 isotope that will remain after 15 years, and then how long does it take for cobalt-60 to disintegrate to the point that there's only 2% of the original amount left, okay? And so how would we solve this problem? I'm going to pause it here, and I will write a little bit on the board and maybe see what you can do with this. I think that, for starters, remember that you have these equations, right? So first, to find the decay constant, you just use this equation here. And we have the half-life, right, of 5.27. So just plug and chug, and that'll give you A. For B, to calculate the fraction of a sample, you just need to use essentially this equation in some form. You have, what do you have? You want to find actually NT over NO. So you can set it equal to e to the negative KT, because we'll have K in part A, or lambda in part A. And the time, right? This time is 15 years. And then for C, you'll want to use this equation here, okay? Because they're asking for what? They're asking for how long does it take for a sample to disintegrate to where there's 2% left. So you could just plug in, you're solving for T by just plugging in 2% of your original amount over what? The original amount. And that should give you time, okay? So let's pause it here, and I'll let you guys see what you can come up with, all right? I'm going to first of all, I'm going to pause it, and I'm going to get rid of this sun, because it makes it impossible to see the board behind me. I don't know if I stopped my recording or if I just paused it. I guess I'll find out soon enough. Okay. Anyway, so they want us to find the decay constant, and then they want to know what fraction of cobalt-20 is left after, what was it here? After 15 years. And then they want us to figure out how long it will take for cobalt-60 to disintegrate to where there's only 2% of the original amount left over, right? And so what I've written here is, for the first part, this is the equation for solving for the decay constant. It's simply the natural log of 2, or 0.693 over the half-life. So it's 0.693 over the 5.27 years, which we've now learned is the half-life of cobalt-60. And so that gives us 0.132 to the negative y, or per year, all right? so that is going to be our lambda or our k that we can put into the subsequent equations that we're going to use. So for b, to find the fraction, we need to look at this equation, okay, where the amount of a sample at a given time is equal to the initial sample times e to the negative lambda t. And to make it a fraction, we can just, where's my green? We can rearrange, we can divide both sides by NO, right? And that will give us NT over NO equals E to the negative lambda T. All right. We know what lambda is now. It is going to be E to the negative 0.132 per year times T, which is, I think it says 15 years. Okay. And so that fraction, that ratio of what's left versus what was initially there, is going to be 0.1, or is going to be e to the negative 0.132 times 15. Okay. And if you do the math there, which hopefully by now, right? Hopefully by now we know how to take e to the something. It's basically when you're flipping around to get rid of that natural log, because this is a first order reaction, and first order reactions have natural logs, then we end up getting 0.138. Okay. And for C, we just take that other expression of that initial equation that I went over, that relates time and the amount of sample. Okay. And so time is equal to a negative 1 over lambda, or I just condensed it all to make it a negative NT over NO divided by lambda. Okay, and they said that they wanted to know how much was left, or what were they asking? They're asking for time when, how long does it take for there to be only 2% left, right? And so that would be, a negative 0.02 for 2%. It looks bad. Sorry. 0.02 times n to the O, right? Our initial over NO, all over, what was it? 0.132. Okay. The NOs are, of course, going to cancel, and we end up getting, what is it? 29.6 years. So that's how long it would take for there to be 2% left. All right. So hopefully that, I don't know, makes sense. That's using this as an example. And this came from the book. So there's a little bit of explanation with the problem. So if you're still kind of hung up on how I did this, maybe check it out in the chapter and see how they describe going through this process. But now let's move on. Oh, I'm sharing the wrong thing. That's the textbook. Here. Okay. So I also I wanted to throw this in here. I guess I probably maybe should have thrown this in a little bit earlier, but this is just showing how you can substitute the concentrations in the integrated rate law for n, which is what we did in the last, basically the last step of that last problem. Whereas n represents the number of nuclei, or the moles of the sample. And I just wanted to throw this in here because, again, it shows this K here. So again, oftentimes that K is changed to lambda to represent decay constant. But you'll see problems where it's interchangeably designated as lambda, or just still denoted as K. So just keep that in mind. Don't get confused when you see the K and you're like, well, wait a minute, what happened to the lambda? They're the same thing. Let's try another problem. So plutonium-236 emits alpha particles and has a half-life of 2.86 years. And if we have a sample that initially has 1.35 milligrams, what is the mass after 5 years? Okay, so I'm going to pause it here and see if you can come up with this, and we'll go over it in just a minute. Okay, so there we go. I've written down some of the things that were given to us in that problem. Time is 5 years, so they want to see how much is, I think, left at 5 years. The half-life of plutonium-236 is 2.86 years, and the NO, or the initial amount, is 1.35 milligrams. Okay, and so they want to find out how many milligrams do we have once 5 years has elapsed, given this half-life of 2.86. So what are we solving for? We're solving for NT, right? What do we need first? Well, we need the decay constant. And how do we do that? We set up the, we say that let's use another color. Say that the decay constant is equal to 0.693 over the half-life, t to the half, or t subscript 1/2, or in this case 2.86 years. Okay, and so 0.693 divided by 2.86 gives us 0.242 per year. Okay, so now we have that. All we have to do is solve for NT. Okay, and remember that we can arrange it to say, we can say that NT equals NO times e to the negative lambda t, right? We have NO, we have now our lambda, and our time is 5 years. So NT, which is what we're solving for, and how much is left, is equal to 1.35 milligrams times e to the negative lambda, which we said was 0.242 per year, times 5.00 year. Okay. Yeah. That's yeah, that's fine. I mean, right there, but that looks good. I think that's legible. So 0.242 per year times, not plus, that looks kind of like a plus, times 5 years. The years cancel, and we end up getting NT equals 0.402 milligrams. Okay. That's the answer for that. Oh, what's going on here? Okay, so this brings us to radiometric dating. Okay, it's not some kind of archaic dating system where we talk to each other over the radio, which you guys are probably not even old enough to even get that joke, but there were actually hookups that occurred via the radio before the internet, which I was. I just happened to be alive and sentient enough to remember life before the internet. So anyway, that probably just didn't land. But no, radiometric dating is using radioactive isotopes to figure out how old things are. And remember, radioactivity is a natural component of our environment, right? We've talked about how the ground beneath us contains radioisotopes such as radon, that break down from uranium-238. I mentioned that the food that we eat, such as bananas that have radioactive potassium, are so it's the food we eat and just our environment, and of course the radiation that escapes the atmosphere that does a great job of deflecting most of the radiation. All of those things are bombarding us constantly, right? And absorbed into our blood, into our bodily fluids, incorporated into our tissues. And so, luckily, living organisms on this planet have evolved to adapt and survive this radiation exposure to a certain extent, of course, right? But it's definitely it's not a benign exposure. It's doing something to our chemical makeup, right? Now we've said that that for any given radioisotope, the intensity of radiation that's produced is directly proportional to the rate at which it's going to break down or decay, right? As well as the amount of the substance. So the intensity of radiation is proportional to the rate of decay, as well as how much of that substance is around, right? And that's how we know it's a first order kinetic reaction. And I also said, to recap on the half-lives, we said that half-lives vary greatly from one radioisotope to another. And in this case, I'm going to talk about radiocarbon dating, but that half-life for carbon-14, as we also talked about, is 5,730 years. And that's only going to get us so far in terms of dating things, because after a while it's going to break down to the point that we can't detect it anymore. But luckily, there are other radioisotopes that have much larger half-lives or much longer half-lives. And the reason that is because, as we've talked about before, each nuclide of a given radioisotope has a specific number of nucleons, of protons and neutrons. And it's going to therefore have its own particular balance of repulsion and attraction, like we talked about last time. The magic number, or the even odd ratios of protons and neutrons. And all of those things are going to come together to form some particular degree of stability within that nucleus, right? And so that's why the half-life of one radioisotope can be so much longer than one of another, because of these different compositions of the nucleus. Okay, and so that means we have to use several different methods to radio date things, but we'll start off with carbon, okay, and we'll talk about it, and then we'll get into another form. Radiocarbon dating came about, I think, in the late 40s. A guy by the name of Willard Libby used it to look at the age of fossils and certain artifacts. And he could do that because carbon-14 is constantly being formed in the atmosphere by nitrogen being bombarded with neutrons. So where's my little spotlight thing? Let's do that. Right. So we have nitrogen in the atmosphere. It gets bombarded by neutrons coming in from outer space, and that forms carbon-14. Okay. And then after that carbon-14 forms, it's going to decay back into nitrogen, but by releasing, right, a beta particle. But that is going to take 5,730 years for half of it to do so. Okay. And what happens is that this radioactive carbon, is going to end up in living organisms. Okay. So what this cartoon is looking at is just nitrogen being bombarded with a neutron here to form a very small, trace amount of carbon-14, and then a little bit more of carbon-13, and then of course the majority of carbon is going to be the C12 isotope that we know and love and have learned and studied so well. Okay, but because this carbon-14 in the atmosphere is continuously being formed and then continuously decaying into nitrogen 14, I guess, if you will, it's basically at equilibrium. Okay, the amount of atmospheric carbon-14 to nitrogen 14. And so what then happens is that atmospheric carbon-14 gets oxidized and turns into carbon dioxide. Well, the carbon dioxide that now has just, all the carbon dioxide is going to have predominantly C12, but just a few molecules by comparison will have the carbon-14 making up the carbon dioxide. That's going to go into the plants, right, when they carry out photosynthesis. And then the animals are going to eat the plants. And so that carbon-14 is going to go into their biomolecules. And then the animals that eat plants are going to get that C14 into their biomolecules. And so what happens is that we end up with all living organisms getting some ratio of carbon-14 to carbon-12. Okay. And it turns out that that ratio is the same as what is found in the atmosphere, right? Um, which hopefully should make sense. And again, it breaks down at its half-life is 5,730 years, right? So we can look at artifacts and, like, for instance, the Dead Sea Scrolls, they were made from once living material like papyrus and wood, and the dyes or the ink to write with is made from other animal derivatives. So you can look at the ratio of C14 to C12 and see how much it's changed, how much it's dropped to date it, right? Um, and so, that is what we use for radiocarbon dating. That's the process, C14 to C12. Now, unfortunately, there's kind of an upper limit of about 50,000 years, because beyond 50,000 years, that ratio of carbon 14 has decayed so much that it's really hard to measure precisely and accurately the amount of carbon 14 in a substance, in an artifact or a fossil. Okay, because C14 is already a trace amount, trace level in the atmosphere. That means it's going to be a trace level in whatever plant, animal, or animal that's taken that in. It's also going to be a trace amount. So if you have a half-life of over almost 6,000 years, and you extrapolate that out about 8 times or so, you're going to really reduce that carbon 14 to from trace to almost non-existent levels. Now, let's see how it works in practice. Okay, so we have here a skull, and we think it belongs to an ancient human, and the carbon 14 decay rate has been determined to be 4.50 disintegrations per minute per gram of carbon, or 4.5 dis per min per G of C. Okay. If living organisms have a decay rate of 15.3 dis per min per G of C, how old is the skull? And keep in mind, like I mentioned, the decay rate is proportional to the amount of the radioisotope, or in this case, C14. So how would we set this up? Well, first, we need to figure out what the decay, what the lambda is, right? What the actual decay rate is. So we could set up lambda equals 0.693 over the half-life. It's C14. So I've said before that the half-life happens to be 5,730 years. Once we get that lambda, then we can, instead of having N0 and NT, we can do what we did when we were talking about kinetics a few weeks ago, where we can set the rates up. Because again, it's looking at how old is the skull. So we're essentially trying to solve for time, but instead of having the natural log of concentrations or the natural log of N0 or NT, we could also think of it as the natural log of the rates. And that's what they're giving us here, okay? These decay rates of 4.5 and 15.3, okay? So first, solve for lambda, and then plug that into the equation where you look at the natural log of the final rate, right? That 4.5 over the initial rate. So rate t over rate 0. The initial rate is 15.3. Okay, I'm hoping that made sense. It's kind of late, so I don't know. I'm off my game. Hopefully, I'm speaking coherently and logically. I feel like I'm struggling a little bit, but we'll get through this. I'm going to pause it, see what you can come up with, solve for lambda, use those decay rates that they gave us to just pop in that equation we've been using all along, and see what you come up with. Okay. So first thing, I just did the simple equation solving for lambda, and that's 0.693 over the half-life, 5,730 years. I get 1.21 times 10 to the negative 4 per year as my my decay constant, or lambda, or k. And then what I can do is I can use this natural log of the current rate over the initial rate is equal to a negative lambda over t. Okay, and so that becomes the natural log of what was it, 4.50 over 15 over 15.3. I'm not going to write out, it's disintegrations per minute per gram of carbon, right? This equals a negative 1.21 times 10 to the negative 4 per year over, times t. We want to solve for t, right? That's what they're asking for, because we're using radiocarbon dating to see how old this thing is. And so we can rearrange this equation to say that t, right, is equal to to a negative natural log of 4.50 over 15.3 over, yes, I can read that, over lambda, which is 1.21 times 10 to the negative 4 per year, right? And so if you solve for that, if you take that all together, you should end up with 1.0 times 10 to the 4 years. Okay. And that's how we do that. And that's, again, in our limit of detection for C14 radiocarbon dating. Okay. Here's another problem. We find a tiny piece of paper, and of course, that paper was made using a plant that was once alive. And it comes from the Dead Sea Scrolls and has an activity of 10.8 disintegrations per minute per gram of carbon. If the initial C14 was 13.6 dis per min per G of C, how old is this Dead Sea Scroll tiny piece of paper? All right, so it's basically the same problem. You got to find lambda, and then you've got to set it up with the rate t over the rate 0, right? So the 10.8 over 13.6, and come up with your answer. Okay, so let's try it. See what you can do. Okay. Really, I'm just going to leave what I have up from the last problem and just replace a couple numbers here. But the lambda is the same because we're still talking about C14. So it's still going to be 1.21 times 10 to the negative 4. We're still going to use this equation. We just got to change the dis per min per G of C, right? And so that's going to, of course, give us something that's slightly different. Okay. So what was it? It was 10.8. So 10.8. And initially it was 13.6. 13.6. So everything's the same except for that rate t over rate 0. And so if you did the math on that, that is 1,910 years. Okay. And again, well within the limit of detection for carbon-14. So now, remember that I said that we can only use this for things that are about 50,000 years old or so. That's why, to look at things that are older, we use uranium lead dating. Okay. So we can use this to look at things that are much older, like rocks, the age of this giant rock, the third rock from the sun. We can use uranium-238 and this decay series to determine how old things are. Because if you remember this decay series from last lecture, uranium-238 eventually breaks down into something stable, and what is stable happens to be lead-206. Okay, and that process takes a long time. It takes 4.5 billion years actually, for a half-life. Okay, so amazingly, we can use that to get at these really old aspects of our universe. And you know young Earth arguers that think the Earth is only about, I don't know, 5,000 years old, they claim that, one of their arguments is that, well, radiocarbon dating is a flawed science. It's not precise. And I mean, I've heard that argument from people in person. I've argued with people about this, and it is imprecise, yes, if you're trying to figure out how old the Earth is, because it only goes to about 50,000 years, which is already 10 times longer than what young Earthers, believe the Earth to be. But then you can say, yes, we don't use radiocarbon dating to date everything. We just use that for certain living things. Okay, we use uranium-238 to lead-206 to look at things that are much older, because the half-life, again, is 4.5 billion years. Okay. And so, because this takes so long, we have looked at rock on every single continent of Earth, and we've shown that those rocks are at least 3.5 billion years old. And what else have we looked at? We've looked at meteors, right? Or meteorites, and we've found meteorites on the planet I guess now I think it'd be meteors, right? Meteorites burn up. Meteors actually land. Or I guess meteorite. I guess you can get fragments of meteorites landing on the Earth. Anyway, that's a geology thing. But we've looked at rock that has come from outer space. Let's put it that way. And we found some of these rocks to be 4.5 billion years old. Okay, so we know that these meteorites that were formed at the same time as our sun, right? Our solar system, which happens to include Earth, all of that is 4.5 billion years old. Okay. But as the great LeVar Burton used to say on Reading Rainbow, you don't have to take my word for it. I don't know if you guys have ever watched Reading Rainbow. It was on when I was a kid. Great show. I can't get my kids to watch it, of course. They won't watch any of the shows from my past, like Mr. Rogers or Sesame Street, you know, the classics. Although I can get my 8-year-old to watch He-Man, and I feel like that's a major accomplishment, and Voltron. But Reading Rainbow, not so much. Great show. Anyway, I need to focus. Don't take my word for it. Let's use a problem to prove that what I'm saying to you is in fact able to hold up when we apply a little bit of math, okay? So here, a meteor contains 0.556 grams of lead-206 to every 1 gram of uranium-238. Assuming that the meteor did not contain any lead-206 at the time of its formation, so meaning it didn't already have any lead-206 in it, how old is that meteor? So all the lead-206 presumably has come from decaying uranium-238. And we said that the half-life of this uranium-238 is 4.5 billion years. So how old is that meteor? Well, what do we have to do? Same thing we've been doing. We have to find lambda, so 0.693 over 4.5 billion years, and that's going to give us our lambda. And then for this, we actually need to do a little bit of stoichiometry, okay? So we know that there is 0.556 grams of this to every 1 gram, but we don't know, that doesn't tell us how many grams we have, you know, initially, right? To have gotten that amount of lead-206. So to do that, you just do some stoichiometry, right? 0.556 grams times 1 mole of lead-206 over its molecular weight, which, what's the molecular weight of lead-206? It's 206 times 1 mole of uranium-238 over 1 mole of lead-206, right? Times the molecular weight of uranium-238 over 1 mole of uranium-238. What's the molecular weight of uranium-238? Same thing. It's 238 grams. And if you do all that, that will give you grams of uranium-238. Okay? And so that way you can plug that into your N0, right? Your NT is going to be 1 gram. Your N0 is going to be 1 gram plus whatever that initial starting material is. Okay? And all of that is going to be over the lambda that you solve for. So again, I hope that makes sense. If it doesn't, well, try it anyway. Same thing we've been doing here with a little bit of stoichiometry, and we'll see what we come up with. Okay. All right. So in that little break, my 2-year-old Theo woke up, so I had to go in there and try and coax him back to sleep. It's about 1 o'clock, and he usually doesn't sleep through the night. anyway, so it was about that time. So hopefully I stay on track and it's not too disjointed after that, because I was just sitting there trying to get him back to sleep and was thinking about Reading Rainbow, and then the opening song to Reading Rainbow got stuck in my head, which is a catchy little tune if you're familiar with it. But yeah, so okay, getting back to this. Oh, and also LeVar Burton of Reading Rainbow was in Star Trek The Next Generation. You may know him from that. But anyway, back to this problem. Uranium lead dating. So again, we have to find the decay constant, or lambda. And so we just take 0.693 over the half-life, which we said was 4.5 billion years. And that gives us 1.54 times 10 to the negative 10. All right, that is our lambda. And then I said to figure out the amount of starting material of uranium-238, we have to do some stoichiometry. So they gave us, what was it? I said 0.556 grams of lead to every 1 gram of uranium-238 was measured, right? So we can say that if we have this, then let's just convert it to grams of uranium-238. So let's go 1 mole of lead 206 over its molecular weight, which is 206 grams of lead 206, times 1 mole of uranium-238 for every 1 mole of lead 206. Okay, that's getting kind of hard to read, but 1 mole of uranium-238 over 1 mole of lead 206 times, what's that? The next is we have grams, so the 200, the molecular weight, right? 238 grams of uranium-238 over 1 mole of uranium-238. I think that should do it, right? Let's see what cancels. The grams of lead 206 cancel. The moles of lead 206 cancel. The moles of uranium-238 cancel, and that gives us our units, grams of uranium-238. Okay, so if you do 0.556 divided by 206 multiplied by 238, we should end up with 0. It's kind of hard to write like this. 0.642 grams of uranium-238. Okay. Now we can plug this information into our equation to solve for T. Okay. If we rearrange the equation we've been using this whole time, we can get T is equal to a natural log of, what is it? It's NT over N0. So the N currently over the initial N. And that's negative all over lambda. Okay. Yeah, that looks legible. So that's equal to a negative natural log of what is our NT? It's now 1.00 grams. Our NO is 1.00 grams plus 0.642 grams. Okay, so it's what we have now plus what we determined must have been around to get this. Okay, and then all of that over our lambda, which is 1.54 times 10 to the negative 10 per year. Okay. So, yeah, that looks right. So if you do all that, solve for t, we get t equals 3.2 times 10 to the 9th, or 3.2 billion years. And that's a long time. So that's our answer, 3.2 billion. Now, one more problem, and then we'll wrap it up, okay? An igneous rock, so rock from a volcano, contains 9.58 times 10 to the negative 5th grams of uranium-238 and 2.51 times 10 to the negative 5 grams of lead-206. And then, basically trace amounts of lead-208. Determine the approximate time that the rock formed, okay? So same process. So you can do the same thing, okay? And, really, I'm going to do this another way, just to show you that there's more than one way to get these answers. And then, but do whatever you want, do it however you want, see what you come up with. And, either way, if you do it the way we previously did it, it should turn out to be the same, but we'll see. We'll do one more and then we'll wrap it up. Okay, so nothing's changed with our decay constant because we're using the same radioisotope, uranium-238 to lead-206, right? Half-life is 4.5 billion years. So I said I was going to do this a slightly different way. I was just going to do it looking at moles, okay? Because why not? We said that, what was it? It said that initially there was a rock that had, or not initially, but a rock had 9.58 times 10 to the negative 5th grams. So I'll write that down. 9.58 times 10 to the negative 5 grams of uranium-238 and 2.51, not grams, 2.51 times 10 to the negative 5 grams of lead-206, okay? Let's convert that to moles. So we would just times this by 1 mole of uranium-238 over 238 grams. All right. And then this would be times 1 mole over 206 grams. Right. And so those two numbers should be 9.58 divided by, that's 1. So 4.03 times 10 to the negative 7 moles of uranium. And then this down here is 1.22 times 10 to the negative 7 moles of lead. Okay. And then remember what we did. We can now see how much was originally present by adding this up. So if we take 4.03 times 10 to the negative 7 of uranium plus 1.22 times 10 to the negative 7 of lead, we get 5.25 times 10 to the negative 7 moles of U total. Okay. And so now we just use again our equation of T equals a negative natural log of NT over N0 and solve for T. Right? So what color should I end on? Let's do blue. So T equals a negative, what? A negative 403 times 10 to the negative 7 over the addition of those two, right? Because it's NT over N0. N0 is our initial. So our initial is the addition of this, so what we started with, right, initially. So over 5.25 times 10 to the negative 7. And that's, we got to do the natural log of that, right? And then that's going to be over 1.54 times 10 to the 9, no, 10 to the negative 10 per year. Okay. So if you do the math there, you should get 1.7 times 10 to the 9 years, or 1.7 billion years. Okay. So there's two ways to do that. One, doing the stoichiometry all out in one long strand, like I did in the first problem, and then getting grams and adding that. Here, we're just converting to moles and adding the moles up. But as you can see, there's always more than one way to skin a cat. And that is how I'm going to wrap up radioactivity. Okay, it's been fun, it's been real, but next we're going to completely shift gears and go into organic chemistry for next week. So if you have any questions on this, please let me know. There'll be a homework assignment with these kinds of problems, as well as the problems from the previous lecture to help kind of reinforce this. But hopefully it's all pretty straightforward. It's basically that same equation we've been using this whole time. So anyway, that wraps it up. Take care. I'll see you next time.